All right, let's get started. Today we're going to be talking about model comparison, how to choose between different. This thing die again? All right. How to choose between different models using STAN. And I need to have to explain that I'm an employee of Columbia University. Columbia develops STAN. Also use STAN for business purposes, and those two things together invoke the Columbia University conflict of interest policy. So before we can talk about model comparison, we need to talk about some of the warnings that you might see from STAN. So I had these next few slides to talk about a couple different times over the past week or so, but we never got to them. So we need to talk about them today, because before you can even analyze the results of a model or compare it to some other model, you need to make sure that all the models that you're estimating are not problematic. And the first and maybe the most disturbing of the warnings that you might get from STAN refers to divergent transitions. Now, remember when we talked that week about what STAN does in Markov chain Monte Carlo, so no U-turn sampling is only using first derivatives. That's sort of the thing that goes along with Hamiltonian physics. And these first order approximations, they're fine even if you're dealing with, a curved surface like a posterior kernel. If either the second derivatives are constant, which we can't guarantee because that all depends on the data and the model and everything else, or the discrete step size that is being used instead of continuous time is sufficiently small. And that is what we can exercise control over. So if you're in a case with a posterior distribution, the second derivatives and the cross partial derivatives of the log kernel for different parameters across the parameter space, when those are not at all even close to constant, for some areas of the parameter space they're different from others, then STAN can unfortunately quite easily, with a finite number of iterations to work with, tune itself into a situation where the step size it uses for the second half of the iterations, which we keep, as opposed to the first half of the iterations, which we call warm up and throw away, the step size that it finds in the warm-up period might not be sufficiently small for the entire parameter space. And when that happens, when the step size is too big and the no U-turn sampling in Hamiltonian Monte Carlo is deciding what direction and how far to push theta as it's going through its leapfrog process, if the step size is too big, then numerical error accumulates in the Hamiltonian process. It's no longer sufficiently close to the true Hamiltonian. And if this gets bad enough, which is not particularly hard to do, some of the parameters may essentially go off to infinity. They just fly off the surface defined by your posterior kernel. And that is not legitimate. It doesn't necessarily mean there's anything wrong with your posterior distribution, but it means STAN is having difficulty drawing from that posterior distribution. And when this occurs, there'll be a warning about there was some number of divergent transitions, and it will suggest to increase the value of adapt delta. So adapt delta, when it's closer to 1, that will encourage STAN to take smaller steps. When it's farther away from 1, that will encourage STAN to take larger steps. By default, it's 0.8 in STAN, but the models estimated by the RSTAN-ARM package will have a higher default in order to make it less likely that you run into these divergent transition problems. But sometimes you will, even when using rstand-arm, even though those models have been coded to try to be as numerically stable as possible. And so when you see that message, the first thing to try is to try it with a higher value of adapt delta, and it'll print out what a value of adapt delta it was using. So you need to choose some value between that and 1. But even if adapt delta gets very close to 1, there may be no sufficiently small step size that allows Stan to efficiently draw from this posterior distribution that's written. And you may need to think about reparameterizations to your model that have more reasonable second derivatives. It's sort of amazing when people are first starting out that there are multiple equivalent ways to represent a posterior distribution for the things of interest. Some have, you know, higher second derivatives, some have lower second derivatives, and so you can get very different performance in the sampling depending on which parameterization of the model you use. Now, with rstand-arm, the parameterizations are already built in and compiled, so you can't really change them without, you know, getting into the source code and recompiling the models. But for the most part, the models with rstand-arm, either they won't have problems with divergent transitions because they're relatively simple, or if they do, they can be fixed relatively easily by increasing adapt delta a little bit. But when you start to write your own Stan programs, oftentimes on your first attempt, you know, there'll be warnings about divergent transitions that you might need to address. But basically, again, this doesn't imply there's anything wrong with your posterior distribution or that the model doesn't fit the data, although both of those things can also manifest themselves in divergent transitions. Or, you know, maybe you've defined a posterior distribution that is improper or things like that. But it can definitely happen with perfectly valid posterior distributions. It's just those posterior distributions, their curvature makes it difficult for Stan or frankly anything else to draw from that parameter space according to the posterior probability in an efficient fashion. Now, Stan, because it can detect these divergent transitions, can at least make a warning about them. If you use Metropolis or Gibbs sampling, you tend to just, and you define a posterior distribution that has characteristics like this, you'll just tend to get draws that are, you know, biased for the true posterior functions that you're trying to estimate for any finite number of draws. So this is a case where the warnings are helpful, even though a lot of people, when they first see them, are really frustrated. Like, they run a Stan model, it takes a long time, and then at the end of it, it basically says, well, you have to rerun it all again with a higher adapt delta. But doing that, even if there's like one divergent transition, can really help you eliminate some of the fourth source of uncertainty that we were talking about the first week or two. Is the software working as advertised? It's not working as advertised when there are warnings about divergent transitions. Sebastian.
Is there anything you can do without the running, so running like a subset of your data, or would that?
Well, that will certainly make it go faster for a lot of models. You know, typically, we'll talk about this a little bit more later today. I mean, you want to use all your available data if possible.
Could an error occur, like develop, I guess, like this sort of thing, that develop once you put all the data, but not the entire subset?
Yeah, that is also possible, particularly if you sort of estimate a flat model, but you need to be estimating a hierarchical model when you put in more observations from more groups and the groups have more heterogeneity, then yes, you might find that your model, you know, either doesn't fit that well or it's hard to sample from. So divergent transitions is probably the worst one. The least bad one is about maximum tree depth. So when the step size is very small, the no U-turn sampler may need to have many small steps in order to get across the important or the typical set of the parameter space till it gets to the U-turn point, and then it can stop and take a draw or randomly draw one of the places it's been on this trip across the posterior distribution. But when you're taking very small steps, it takes a lot of those steps to get to the U-turn point. And sometimes when you do that, the no U-turn sampling doesn't actually U-turn. It hits its threshold, which by default is 10 steps without U-turning. So it sort of starts all the way on the left, takes 10 steps in the direction of the right, but never actually U-turns by the 10th step. And so when this occurs, there'll be a warning about max tree depth, suggesting to increase that. The default in regular stan is 10. In RStan ARM, it's bumped up to 15, again, to make it less likely that you see this message. But sometimes you will, in which case you should probably increase max tree depth by like 1. And it will, probably be fine. But be aware that when you increase max tree depth by 1, you're basically going to be doubling the runtime because it actually does 2 to the number of steps evaluations of your function every iteration. And so if you increase that from 15 to 16, you're doubling the number of function evaluations that Stan has to do if it's hitting its limit. Now, a lot of times, their posterior distributions, it U-turns before it reaches the maximum, in which case it's using much fewer than its maximum number of function evaluations. But generally, when you're hitting up against the ceiling, you need to be letting it run longer or maybe try to take larger steps. But if you've already hit divergent transition warnings, and that's why you're taking small steps, then oftentimes you also have to increase max tree depth by 1 in order to make sure that the no U-turn sampler can actually get to the point where it makes a U-turn. And then you've basically covered with one sort of sweep the whole subset of the parameter space that has a positive probability of being selected. So this is a very easy thing to fix, although it takes twice as long when you do so, but it's very reliable once you get the large enough tree depth. Questions about either of those? No? Okay, the next warning that you might see is about the low Bayesian fraction of missing information. And this can happen when the tails of the posterior PDF are very light. So when the tails are heavy, you tend to have divergent transitions unless your adapt delta is high enough. When the tails are less light than a normal distribution, again, that can be problematic, and not only for no U-turn sampling, but for Metropolis Hastings and everything else. It can not get the tails of the posterior distribution right. And when this occurs, it will manifest itself in a warning message about Bayesian fraction of missing information being low, or BFMI. And when this happens, it's usually also going to go along with small values of effective sample size for one or maybe all of the parameters. Basically, it's another indication that although there may not be anything wrong with your posterior distribution, Stan is having difficulty getting a good effective sample size for a model like this. And in a situation like this, there's not a whole lot you can really do. One thing that you can do is just increase the nominal number of iterations. And if the effective sample size is only 5 or 10% of that, well, that's not great, but you can increase S to the point where you're getting enough effective sample size. But a better solution would be to think about reparameterizing your model to make it easier for no U-turn sampling to move throughout this posterior distribution, posterior kernel efficiently. Again, with RStanArm, sort of the good and bad aspect of it is that it comes with models pre-written, and frankly, those are unlikely to trigger the warning about a low Bayesian fraction of information. But when they do yield warnings, all you can really do is mess with the settings, maybe mess with the priors a little bit, but you can't go in and change the reparameterization without like recompiling the whole package. And we haven't really learned yet, we will in April, but we haven't really learned yet how to write a whole Stan file to define your posterior kernel and all this stuff so that Stan can draw from it. We've done a good bit with the Stan language on the homeworks and in the lectures to write functions in the Stan language that just do like one piece of it, like draw from the prior predictive distribution. So that's like step 2 or 3 on the Bayesian workflow. But one of the ones toward the end is, draw from the posterior distribution with, wild data. And that's what RStanArm does, but it has programs that someone else has written. We'll soon, or another month or so, get to the point where you're writing your own whole Stan programs in the Stan language, and those can be whatever you want. That gives a lot more flexibility to do research and modeling, but it entails you're going to see a greater proportion of the time warning messages like this. Becca.
Is S, I know we've been using S as the number of draws in our models. Is that the same as the number of iterations, like when it says
it's half, so it throws away the first half as warm up. So by default, it's 2,000 iterations, throws away the first half. So S would be 1,000 per chain, and by default, it does 4 chains, so 4,000.
So that's, but S is iterations.
S is iterations you keep. Other questions? No. Okay, so once you do this, and there's no more warnings left, or maybe there weren't any to begin with, then you can go on and start analyzing the results, making posterior predictions, comparing models to other models, things like that. There's actually one more, which is not really a warning message, but an informational message, saying that sometimes this parameter is supposed to be positive, but it turned out to be 0, or some parameter should be finite, it turned out to be infinite, or some things should be, a number, but it was actually NaN. What these mean is there's been underflow or overflow in the numerical evaluation of your posterior kernel, or the gradients, or something like that, which basically means that for 64-bit computers like the ones that all of your laptops are, it couldn't represent the true number accurately. So if you go into R or whatever, sort of the biggest number that R can represent is something like 10 to the 324th or something like that, which is like way too big for normal use. But if it's one bigger than that, R just calls it infinity. And Stan does the same thing. It's not really specific to the language you're using. It's specific to the hardware on your computer. It can only represent so many digits using 64-bit numbers. And the same thing can happen to 0. You might get a number that is so close to 0 that the computer basically just rounds it to be exactly 0. And if that happens, and let's say that's like a standard deviation or a variance, you may get a message from Stan saying, hey, this variance parameter was supposed to be positive. but I got a 0. So I can't evaluate this function. And so when that happens, there'll also be a message. You don't see those in RStan ARM. If any of them occur, we just don't show them on the screen, just because the models in RStan ARM, we know that they've been coded with as much numerical stability and accuracy as we can get. And so if like 1 or 2 times that breaks down, particularly if it's during the warm-up phase, it's not that big a deal. But when you write your own models, you may see this more often, and that's an indication that maybe you should try to use functions that are more numerically stable to accomplish what you're doing, and that is discussed a lot in the Stan user manual, which we haven't really gotten into that much yet. But these definitely, if they're just in the warm-up phase and there's only like a few of them, you don't really need to worry about those at all. If there's a lot of them and they happen after the warm-up phase, then maybe you should be more concerned about them. But anyway, once we get past all that and we have different models that seem like at least computationally they're okay, we immediately come to the question of, what model is best. And that entails evaluating what model is best on what criteria. So a lot of you were in the data mining class with me last semester, and we got a ton of exposure, especially the second half of the semester in the fall supervised learning models, about how we choose which model to go with. And in general, supervised learning, machine learning, very concerned about the decision to use one model or one procedure over another, or over 100 different ways that you could possibly obtain predictions from the model. And they're also very concerned with making the criteria for deciding what model is better than another to be prediction accuracy or classification accuracy. Nothing to do really with directly speaking with the parameters in the model, but only what predictions they imply. And there's also a very strong convention when doing one of these supervised learning things of separating your data. Maybe like 75% of the observations you use in the training data set, those are the ones that you minimize some function to obtain parameter estimates, and leaving maybe the other 25% or so, doesn't have to be exactly these percentages, as the testing data set, where those observations are not used to influence the parameter estimates. They're only used to obtain predictions, and then you compare the predictive accuracy of different models in the testing data set. And one of the things that we talked about the first day or so is that this creates an issue that, well, if you sort of take the first 75% of the observations, call those training, the last 25% testing, you may find that the first model that you estimate was better. But if you switched it around and did like the first 25% of the observations testing and the last 75% training, estimated your models on the training data, predicted into the testing data, you may reach a different conclusion as to which model is better. And that would seem to be, kind of a quandary. But the machine learning people mostly avoid that by, only doing the splitting into training and testing once, even though the answer that you get out of that may be fairly arbitrary, and it may be, not even the majority of the ways to separate into training and testing yield that answer. And that kind of goes along with the fact that most of, although not all, but certainly all the stuff that we talked about last semester are really probably all the stuff that you would encounter in an undergraduate or a master's level class on machine learning. doesn't attempt to quantify the uncertainty in anything. So doesn't attempt to quantify the uncertainty in the parameter estimates, doesn't attempt to quantify the uncertainty as to which model is best, doesn't really attempt to quantify whether the software is working correctly. Really all you get are these point estimates, point predictions, and the ability to evaluate some loss function of the predictions over the observations in the testing set. But because you don't get you just get like one number for each of the coefficients in the model, there's not any real built-in way to quantify the uncertainty in anything. On contrast, for Bayesians, they're sort of equally obsessive about keeping track of all the uncertainty in the parameters, in what model is best, in the loss functions, as best they can, and to represent that uncertainty with probability distributions. And you don't hear from the supervised learning literature as much talk about probability distributions, particularly with the sort of introductory textbook that we were using last semester. Also, there's a pretty strong inclination among Bayesians to condition on all the available information, all the available data that they have, in order to get a posterior distribution that is the most concentrated and gives the least amount of uncertainty about the parameters that they're trying to do. And so it may have occurred to you last semester that this idea of, well, separating your data into 75% training, 25% testing, or something like that is kind of an expensive way of getting some observations that are in the testing data set that are not implicated in the parameter estimates when you don't have a whole lot of data to begin with. Now, in fairness, most of the supervised learning things that we were talking about last semester were envisioned for situations in which you have so much data that the uncertainty about the parameters is going to be small or maybe negligible compared to your uncertainty about what model to use. And so this idea of, well, if we have 4 million observations, we'll use 3 million for training and 1 million for testing, but the uncertainty about the parameters after conditioning on 3 million observations is so small relative to the question, what model should we use? And in that scenario, okay. But if you have 40 observations, then one separating into training and testing that has only 30 in training, it's going to make a bigger difference in terms of the uncertainty around the parameters. And also having only 10 observations in testing again means there's going to be a lot of noise in which model gets selected if you only do the splitting once. And if you do the splitting more than once, then there's additional concerns about overusing the data and things like that. But this idea of, well, just routinely only use 75% of your data seems intuitive-ish if you're coming at this perspective, well, I'm just going to ignore all the uncertainty in the parameters anyway. So why does it matter if I only use like part of my data or all of my data, when I'm just basically assuming that the uncertainty in the parameter estimates is going to be negligible? Now, that sort of attitude doesn't really hold for a lot of situations in the social sciences, although there's certainly large data sets in the social sciences as well. But we're rarely in the situation where we're talking about millions of observations. Sometimes, but more hundreds or thousands would be kind of typical for survey research. But if you're doing stuff on institutions, then you may have much fewer observations than that. So this idea of, well, we'll just hold back 25% of our observations is an expensive solution to this problem of, well, we don't want to use the same observations to decide what model is best that we use to estimate the parameters with, because when we do that, even if we're estimating a bad model, the parameters will be pulled in such a way that they tend to fit the data that you train on, as well as possible. That's a consequence of optimizing some optimization function. You're going to get the parameters that fit as well as possible for the data that you give it, which leads to this almost, I wouldn't say knee jerk, but very strong convention of separating out the two parts of the data. So it's a solution to that problem. It's kind of an expensive solution to that problem. And I think a lot of the literature on the supervised learning stuff emphasizes this aspect of the problem because, one, that's the one they have a solution to, but also because within the sort of traditional machine learning framework, it's a problem that they created for themselves by using optimization as the estimation technique. So you get back the one set of numbers that is absolutely the best with respect to whatever objective function you're using for those data, and not considering any of the uncertainty in the, around that estimate. It's sort of course, you're going to get predictions that look better in the training data than when you apply the same approach in the testing data, because the parameter estimates you get are sort of overly tuned to the data that you train on. And so that's one of the reasons why adding a penalization component to the objective function helps a little bit, because it makes the estimates less sensitive to the data, because they also have to worry about the penalization thing. But this problem can be mostly avoided in the first place by not using optimization as your estimation technique, by using sampling from the posterior distribution as your estimated technique, in which case you're not getting just the best posterior mode set of numbers and using that for all your predictions. Rather, you're getting draws from all around the posterior distribution in proportion to their posterior probability that reflects or propagates your uncertainty about the parameters into the predictions. And as a result, Bayesian approaches, you tend to get about as good predictions on the data that you condition on as data that you don't condition on. And if that's true, you might as well condition on all the data that you can get your hands on in the present. So I don't want to say that it's like not a problem to evaluate your models on the same observations that you use to condition on. It's an issue, but it's not really a huge issue. In my mind, the first primary issue is this choice of whether to use just numerical optimization or basically numerical integration by drawing from the posterior distribution rather than taking just one set of numbers. And I think that is a real fundamental difference between the supervised learning approach to model comparison, which those of you who were in my class last semester should be familiar with, because we did it every week for like half a semester, versus what we're going to talk about the rest of today. Question, Salif?
I don't know much about the optimization process, but is there not also maybe you can just send a summary how that works? It's what I have to imagine is maximum likelihood. Is that?
Oh yeah, so maximum likelihood is one method of numerical optimization. What the computer science engineer, non-statistician people tend to do is take a likelihood function and also add on a sum onto that, a penalization thing that discourages the parameters from being too far away from zero. That tends to yield better predictions in the so-called testing data than maximum likelihood alone. So there's lots of sort of optimality properties of maximum likelihood that Fisher and people like that derived that pertain to the parameters. But none of those optimality things that maximum likelihood or least squares enjoy pertain to predictions from the model. Really, prediction in the frequentist sense is like not a very important and doesn't even quite make sense thing. And so if you're coming at this from like a less social scientific, maybe more of like a business sort of like, I just want to predict how much I'm going to sell next quarter so I know I can make enough, you know, toys or whatever. And you don't really care about the parameters in the model, only how they predict, then you might go against a pure maximum likelihood and more of like penalized maximum likelihood or lasso, something like that. But what I don't want to give you the impression, and I think a lot of people have this, is, well, if your criteria and stuff like that are all based on the predictions rather than trying to estimate a treatment effect or something like that, you know, that's fine. But I don't want people to sort of instinctively say, well, if I care about predictions, I have to do some machine learning thing. And if I do an experiment, I have to do randomization inference. And if I have a survey, I have to do frequentist inference, because drawing from the posterior distribution can apply to all of those situations. Like you can do Bayesian inference, and if you just care about predictions, well, make your predictions. In a lot of ways, that's going to be better, and it's certainly going to be a more general thing that, you know, once you get some more practice with, then you can apply it to, you know, whatever situations you find yourself in. Maybe sometimes you care mostly about predictions, other times you compare about a treatment effect estimate or things like that. And so that's one of the real advantages, I think, of learning the Bayesian approach, is because it's so flexible, it's so general, and it's at least, you know, a good candidate, you know, to be applied in any situation. So if we go back to this diamonds example, remember we used Stan LM to estimate a model. We had the number of carats. This is all in log form, you know, interacted with the size of the diamond. We had some other variables for cut and color and clarity, things like that. I used a prior mode of 0.8 when we did this the first time. And here I specified adapt delta is 0.95, and that resulted in having a step size that was not too small, but it resulted in 2 of my 4,000 iterations hitting up against the maximum tree depth. And so what do we do when that happens? Increase the maximum tree depth. So if I made this 16, it would have been fine. But actually 15 is probably fine too. But anyway.
Is there a reason why I would get a different warning message that say there were 3 divergent transitions?
Yeah, different seed. So this is random, but anyway, not a big deal. I could have easily fixed it, but I just wanted to show you like what the message looks like. And instead of re-estimating, I'm just going to ignore it, but you shouldn't do that. So one of the things that we might want to do is then look at the posterior distribution of R squared. And you can see the posterior distribution. It's 1, very concentrated because we have so many observations. 2, it's centered around about 0.985 or so. So that certainly went up relative to the prior that I used, which might seem a little bit surprising to you. But again, remember, these are raw diamonds. And so those are priced more according to like a formula. You would see more noise in the price for like retail diamonds if you buy them on 125th Street or something like that, than you would in this. So this is like the crude oil version of diamonds that is priced on markets and pretty consistently. Anyway, So one of the reasons why the Bayesian approach tends to work, well for making predictions is because we have the prior distribution in addition to the likelihood. And so we can use the prior distribution to discourage the posterior from going to completely unreasonable parts of the parameter space due to overfitting. And there's a pretty close-ish connection between the use of prior functions as part of your log posterior kernel and using penalty functions in a machine learning context. And at least in some cases, you'll find the posterior kernel that a Bayesian uses is exactly the same, or maybe multiplied by -1 of the objective function that machine learning people use. Like that happens with lasso. That can be seen as a Gaussian likelihood in a particular form of a Laplace prior for the penalty function. But the difference, and this is the difference you always have to keep in mind, is that when doing machine learning and you're just finding a numerical optimization, the penalty only matters insofar as it moves the mode compared to an unpenalized function. Whereas the prior distribution affects the entire posterior distribution, not just the mode. Like it moves the median, it moves the mean, it moves the whole distribution a little bit. And so the kind of difference between the way penalty functions are used and prior PDFs are used, again, goes back to this idea that Bayesian's one draws from the entire parameter space in proportion to the probability, whereas the conventional machine learning approach is just interested in the mode of some function. And so the prior that we specified, having a mode of 0.8, discouraged the posterior of R squared from like going up to 0.99 or something that may well have overfit the data. So using priors can guard against overfitting, which is the problem that a lot of machine learning people are worried about. Less so among statisticians, but these days there's a lot of people who don't really come from statistics departments who are doing quantitative analysis. And this function can be made by just calling some functions in the Bayes plot package. We'll see this a little bit more on Thursday, but there's a lot of graphs that we can do to represent our posterior distributions. And frankly, that tends to be better because the answer of the Bayesian approach is really a whole posterior distribution, not just one number that incompletely summarizes this whole thing, such as its mean or its median or its mode. It's really the whole thing, even though this particular case it's pretty concentrated around 0.985 or so. So priors can help avoid overfitting, but it's still so you'll occasionally, this can be a sort of confusing thing. You'll occasionally see someone on the internet saying like Bayesian approaches cannot overfit the data, and what that means is less than it sounds. So if you draw from the prior predictive distribution n times, get the posterior distribution, draw or estimate the parameters after feeding back draws from the prior predictive distribution, and then you do that again, do that again, do that again. On average, over those exercises, the Bayesian model won't overfit. It also won't underfit. It will fit exactly according to the prior predictive distribution that you're feeding back into. With wild data, it is possible to overfit or underfit. However, you should always be able to tell which is the case by evaluating predictions of your posterior distribution conditional on the wild data. So we call the posterior predict function. Again, that is going to yield a matrix that is S by N. I think some of you on the homework, you might have had to reduce the number of iterations or the number of observations just to make it fit into RAM. But in general, it's S by N. And we have, 54,000 diamonds here. So that's why the posterior distribution is so concentrated. And so one thing that we can do is evaluate posterior predictive coverage. So here I'm applying to each column of the posterior predictive distribution. So for each observation, I want to calculate the 25th percentile of the draws. And I do the same thing for upper, counting the 75th percentile of the draws. And so what my model implies is that there's a 50% probability that the outcome that we observe for this observation, these sets of predictors, should be between here and there. But I have 1,000 draws from my posterior distribution that I'm using to capture my uncertainty as to what the 25th percentile and the 75th percentile are. And so if I then evaluate on the actual log data, what is the proportion of times that it comes up greater than the lower bound and less than the upper bound, according to my model, that should be true for exactly 50% of the 53,920 observations. As it turns out, it's true for about 53% rather than 50%. And so this tells me that I might have overfit these data a little bit. And this is a very important, it's also a very Bayesian concept. So I'm going to try to say it again more smoothly. When you get the predictions, these have randomness to them because you're uncertain about the parameters, and so you're uncertain about the predictions. But if you say, okay, here's the 25th percentile, here's the 75th percentile, the predictive distribution, there's a 25% chance it could be less than this, 25% chance it could be greater than that, but 50% chance it's in the middle somewhere. And if you have a bunch of conditionally independent observations, you can just count up the proportion of times that the prediction interval encloses the observed data that you have. And if you make a 50% interval, it should be true that the actual observation falls in a 50% interval half the time. If you made like 33%, 66% window, then it should be true that 2/3 of your observations fall within and 1/3 fall on the other side with 1/6 on each. And so, we can do that in this case, and we had 53 successes falling in 50% intervals. And so that is an indication that, we may have had, too many parameters. There was like 28 of them. Maybe our priors were too weak. But in general, for one reason or another, we're predicting a little bit better on these data than the model implies we should, which is really the definition of overfitting. Even though the degree of it is not that bad in this case, I've certainly seen a lot worse. Rob.
Is this sort of telling us that our posterior distribution is like too dense around the mean or median, I guess?
Too dense around each point. So this is a predictive distribution for each point. So imagine like all of you are observations in my data set. Yeah. I get predictions for Nathan number 1, a whole distribution of those. And I get predictions for you. I get predictions for each of you, a whole distribution. And that distribution is going to have a middle 50%. And what this is saying is that sort of the middle 50% is overly tuned to the actual observations that the data set had in it, which we conditioned on to get the parameters, which we then use to predict. So yes, it is possible for Bayesian models to overfit on wild data. It's usually not an overwhelming amount if you're specifying reasonable priors. But whether it's a big problem or a small problem, you ought to be able to recognize it just from the observations that you have. So you can, but it's definitely not required for you to split your data into training and testing. So if I had split into training and testing, and then I made the predictions in the testing data, and then it took their 50% intervals and counted up the proportion of times that I got the testing observations in my 50% intervals, it would probably be like 47, 48%, because I overfit in the training data a little bit. Stephanie.
Can you see in the data set which observations predicted correctly and
Oh, yeah.
which didn't?
Yeah, it would just, instead of calculating the mean, it would be, make a graph or just return the vector instead of down. And then you could just see which ones that's true, see which ones that are false. And that can help you like diagnose outliers and other things like that. There was a question over here, Andres?
I'm just trying to figure out the margin argument that's doing exactly what it makes.
It's applying the quantile function column-wise. So take each of the 53,920 columns, apply the quantile function, and return the 25th percentile, return the 75th percentile. And so I get vectors of those, and then I can see how often those are the case. Yes.
Okay, so the stuff that you were describing, is it correct to kind of make a parallel between bootstrapping, or is that like
They get lumped together because they both, cause your laptop to burn your legs. They really have not much to do with each other, except for the, second-degree burns. So bootstrapping means take a sample of size n with replacement from the existing data set that you have. And do that over and over again, estimate your thing. What that yields is properly speaking, an estimate of the sampling distribution of your point estimator across data sets. And so if you have a sufficiently large data set, the fact you're doing sampling with replacement rather than sampling without replacement becomes negligible. And you now get this distribution of point estimates across slightly different data sets, which are supposed to represent, how much the data sets would vary from one to the next if you took a real sample from a real population. The Bayesian approach, you don't resample the data. You don't ignore part of the data. You just take the data as given and condition on it every observation once. But we are doing draws, simulations, etc., involving posterior distributions, parameters, and the predictions that they imply. So again, it's this idea of, are we conditioning on the data and estimating the posterior distribution of the parameters conditional on the data, or are we interested in the distribution of the estimator across data sets? Okay, so you should know if you're overfitting, you should know if you're underfitting. And so, okay, maybe I overfit this a little bit, and now I can try a model that doesn't have interaction terms in it. It just has caret additively with log x, log y, log z. I reduced my R squared because I took out the interactions. It's important when you do this to not let the fact that this posterior distribution of the first model that you estimated, it had a center of about 985 or something like this, which is much higher than 0.8. It's when you're comparing models, you can't let the posterior distribution of one influence your priors of the other. So I just basically took my base of 0.8, which I used before, and I said, well, how much would I think I lost by taking out the interaction terms, and then bumped it down to 0.75 or so. But it would have been like not a good idea for me to go up to 0.95 after having seen the posterior that results from the previous model on the same data. So that is definitely one way in which you can get yourself into an overfitting problem, is by using like the posterior distribution of one model to influence your prior for another model on the same data. And that may be one reason why pre-registration of a Bayesian analysis could be a good idea. Go through this again. I get a little bit less overfitting, still some. So it looks as if the overfitting problem probably didn't come from the inclusion or exclusion of the interaction terms. I may have just had like too many categories of cut and color and clarity that maybe I should be collapsing together or whatever. But anyway, I could keep messing around with this until I got my overfitting down to a reasonable level. But it's already actually like pretty reasonable already. And this model fits a lot worse than the previous one. And so that has to be taken into consideration. But at least this one is calibrated better a little bit than the first one that I estimated on the basis of this overfitting percentage. Okay.
I'm still like a little shaky on how do you know to move the location of the R squared in the prior?
Right.
How much?
Yeah. So again, it's subjective, but I started with a value of prior mode of 0.8 when I had the interaction terms in it. So if that's my starting point and then I take out the interaction terms, my prior mode should be like a little bit less than 0.08. And so I use 0.75. What would not have been good would be for me to look at this and be like, oh, it's really 0.95 on the basis of looking at this posterior distribution. Becca?
Seems like you lost a lot and didn't gain very much in doing that.
Yes. And so that's what we want to talk about next. Yeah. Stephanie?
So if you want to, so say you like this model, you're okay with whatever result you get, and you want to try and predict something that you don't have the value yet, like a future thing, do you just put that data set in and just call it and it can?
Yes. So you want to specify the new data argument to posterior predict, giving it, the predictors in the future, and you can iterate this. Like if you have a time series model, you can predict tomorrow and then use those predictions for tomorrow to predict Thursday and things like that. Okay. So the reading for today was all about leave one out cross-validation. So suppose you omitted the ith observation, just one observation, obtain draws from the posterior distribution that has PDF f of sigma given all the y's except the ith, and then you evaluated the log likelihood at the ith observation, so the log likelihood for theta at yi, and you did this for every posterior draw of theta. That would be a good way of seeing how well your model predicts. You'd be conditioning on all the observations you have except one, and then you could predict each observation in turn, evaluate some loss function across those predictions. But in order to do that, you would have to draw from the posterior distribution n times because you have n observations to leave out just one of them and obtain the posterior distribution conditional on the rest of this. And that would take a lot of time to do. It would take a lot of computational resources. It would be, probably unreliable because, something is going to go wrong with at least one of the Markov chains. At least once you would get warning, sometimes about adapt delta is too low, sometimes max tree depth was too low. It would just be a really intensive thing to have to draw from the posterior distribution n different times and obtain, S draws. But what it turns out to be is possible to estimate what would happen if you did all that. And the only thing you have to do, two things you have to do to make that estimate is obtain the posterior draws, conditioning once on the entire set of observations. And then there's one additional assumption, but this is a verifiable assumption, that no individual observation has an overly large influence on the posterior distribution. And so leaving one out only has like a smooth, small, continuous effect on the posterior parameters rather than like a big jump in terms of how it. But you know, that second assumption thing, that's something that we can evaluate. So really, this is an almost free way to avoid all that work. Just estimate your posterior distribution once and still be able to estimate what would happen if you left out each observation, predicted it, and then applied some loss function to those predictions. And so the way in which this goes, or the way in which this is conducted, goes like this. The starting with the posterior predictive density, the PDF of the predictions for a future outcome y, given the past outcomes y1 through yn that you condition on to get the draws. That PDF can be represented as the product of the distribution for the data given the parameters, future data given the parameters, multiplied by the conditional distribution of the parameters given past data, integrating out each theta parameter. Now, of course, we can't do that integral analytically, but conceptually, that is how we could come up with a PDF for a future outcome y. So then the expected logarithm of the predicted density, known as ELPD, not just for one future observation, but for a data set in the future that is the same size as the past data set, can be written as the summation from 1 to n of the logarithm of our g function here, the predicted density of future y given past y. This should have a little n on it, multiplied by marginal distribution and integrated here over future data. So that is a quantity that is the expected log predictive density, and that's what we're able to come up with an estimator for. You could use other g functions, but the one that Bayesians prefer to use is based on this predictive density. And so this quantity, the ELPD, can be approximated under the assumption that I was saying earlier as the summation of the logarithm of the predictive density for the nth observation, conditional on all the other observations but the nth. So leaving out yn when predicting yn. So technically speaking, this looks like it requires you obtain this n different times, but actually you don't have to obtain it ever. That's because we can use what's known as importance sampling. And the idea behind importance sampling, or the reason why we do importance sampling, is this. We want to draw s times from the entire posterior distribution, and that has PDF this. And we want to come up with some way of reweighting those s draws from the posterior distribution to turn them in to s draws from the posterior distribution if we were to leave out one of the observations and, you know, re-estimate with Stan from this posterior distribution, omitting the nth. And so what would the weights be? It turns out the weights are just proportional to the reciprocal of the density for the data, so evaluated at the nth observation, and evaluated at the s draw from the posterior distribution that we obtained when we used all the data. And that 1 over f here can be seen as proportional to the posterior distribution, leaving out the nth observation, dividing by the posterior density conditional on all the observations. So we have these importance ratios R. We have one of those for each observation. And for each observation, we have S of those because we have S draws from the posterior distribution. And then the sum, the weighted sum of the predicted density for a Y value at all the draws for the posterior distribution, weighted by these R things, divided by the sum of the importance sampling weights, converges to this leave one out predictive density as the number of draws goes to infinity. However, this particular estimator is not a great one. It can be pretty noisy for like 4,000 S, etc., because it's using these importance sampling weights that are the reciprocal of something. And so if any of these density values in the denominator here get close to 0, then the R is going to get really close to infinity, and that induces a lot of noise in this process here. So how can we come up with a perhaps biased estimator of these importance sampling weights, even though the bias is actually very small, that has a lot less variance, and then obtain leave one out predicted density that is going to have a lot less variance as well. And we can do that also by fitting a so-called generalized Pareto model to the raw R values that we obtained. So the generalized Pareto distribution is very similar to the Pareto distribution that we talked about in class that one day. It has an extra parameter. But anyway, it's another distribution that is intended to be appropriate for situations that have a long right tail, such as these R values. And so we fit the Pareto model, and instead of using the raw R values that we get, we use the estimated R's that come from the Pareto model when they're like sufficiently large. And doing so does a lot to stabilize the variance under an assumption, and this gets back to the assumption I was talking about earlier, that the estimated shape parameter of the Pareto distribution is not too large. And we actually know what too large is. So anything below 0.5, you're basically, theoretically, that's perfect. If it's between 0.5 and 0.7, you're probably going to be okay. You get one of these for each observation. If it's between 0.7 and 1, that's definitely not good. And if it's greater than 1, then that is basically, you should not use this particular approach. And Lou will suggest, well, for all the ones that are bad or very bad, you actually should leave one out on just those observations. And so if there's like 3 values here that are very bad, the 17th observation and the 24th observation and the 76th observation, we'll leave one out just 3 times, not n times. And then, estimate what the leave one out predicted density for those 3 is directly. And then for the remaining n-3 observations, this approach with Pareto smooth importance sampling can work just fine. So what does that look like in practice? If we go back to this model that we estimated last week of age, voting, and income and stuff like that, and then we just call the Lou function, it does all the Pareto smooth importance sampling stuff that I talked about for you. When you create your own stand models, it's going to be a little bit more complicated than this because you have to give it a matrix of log likelihoods that's S by N because it's not going to know what your model is. But if you do this with stand JLM, Lou knows what model was estimated. It can calculate all this stuff for you. And we get an ELPD estimate of -854. And that can be compared to another model. And values that are higher indicate that model is expected to predict future data better than a model where those are smaller. So if it was like closer to 0, that would be better than negative 854. Like a lot of things, this number has no absolute meaning, only can be compared relatively between two different models. So I want to quickly show you another model, and we'll talk about this more some other time, but for those of you who are in data mining last semester, we had models that had smooth functions of one of the predictors. So rather than saying age is linear, age is quadratic, we can just say, well, there's some smooth function of age that predicts voting. That can be done with the stan_gam4 function rather than stan glm, and so we get post smooth. I had to increase my adapt delta to 0.999 in order to get rid of some warnings about divergent transitions, but after that it was fine. I can make a plot, if I call plot of Lu, of my estimated k hats. Again, all of these are less than 0.5, so I'm good here. My assumption that each of these observations has a negligible effect on the posterior distribution seems to hold, because this only goes up to about 0.1. So we're good there. And then we can call the compare models function, comparing the Lu of the first model I estimated, where age was a quadratic, or voting was a quadratic function of age, to this more flexible model where voting is a smooth function of age, not necessarily restricted to be linear or quadratic or anything like that. We get a difference in the expected log predictive density of 0.3 with a standard error of 0.8. So basically the conclusion of this is you would be essentially indifferent between the two models. They're both expected to predict future data about equally well. And so for ease of explanation, you might want to go with the quadratic one rather than trying to have to explain like smooth functions to whatever your audience is. But if your audience happens to be people who are like allergic to making assumptions, then maybe you want to present the results of a smooth one that doesn't assume anything about the functional form. I'll get to the questions, just one more slide. But part of the reason why there's no real difference in the expected predictive log density of these models is because the effect of age in the 1992 election is basically not very much to begin with, because I can estimate that smooth model. Maybe for very old people, it starts to kind of make a difference, but we have a whole lot of uncertainty, posterior uncertainty, about the effect of age for people who are 80 years old, because there's not that many of them left, etc. Questions?
Can you go back to the graph of the one out?
Yeah.
Yeah, that one. What does it mean then if it's negative?
That's fine. Yeah. Anything less than 0.5, you're good.
Do they have like any different interpretation? Like,
no. It's only the ones that are like bigger than 0.7 that you need to start being worried, but it'll give you a warning when that happens. Nicole?
So where it says all product estimates are good,
yeah.
One of them was bad.
Then it would say like one of these is bad.
But it wouldn't tell you which one.
You could figure it out from the plot. It also is returned. This Lu thing returns a list, and so you can dig into the list and find which ones they are. But if any of these were above 0.5, this plot would have the number of the observation next to it if you select that option. Another question, Robert?
Compare models gives you the EL video of the second one minus that of the first one?
Yes. So the difference here is basically zero. We have some uncertainty because all of this is estimated, and the uncertainty is large relative to the estimated difference. So that's saying, okay, this model is more flexible, so it's going to fit the existing data better. It has to. But because it's more flexible, it has more propensity to overfit, it might tend to predict the future data worse. Whereas this one was less flexible, it fit the existing data not as well, but it's more parsimonious, and so it tends to have, more ability to hold up when you do it. Anyway, what it's saying is both of those things basically washed out. You have two pretty good models that are expected to predict equally well in the future. But a lot of that is because age didn't really make much of a difference in either model. And so what you do on the age variable has not that much of an influence on this ability to predict who would vote Republican in the 1996 election, for example. Now, if we had a more important variable here, then maybe you might see, one being preferable to the other. If the functional form actually was quadratic, then the smooth function would probably capture that, but you might as well just explicitly estimate a quadratic form there and only be estimating 2 extra parameters as opposed to, this, which really estimates like 20 more parameters in order to capture that smooth function without assuming anything other than it's smooth. Okay, so that's all for today. We'll pick it up Thursday. We'll talk about the homework. That's due Thursday. So if you have more questions about that, post on Piazza. And then the rest of Thursday, we'll talk more about these ways of like visualizing stuff from Bayesian models.
Maybe.
Yeah.